the context of an emergency circuit interface, or ECI module, which facilitates the switch from normal power to emergency power during outages, a connection between the normal and emergency power neutrals can indeed enable the system to function correctly. Let's explore the mechanics of this functionality. When normal power is available, the ECI module establishes a connection between the normal hot wire, the normal neutral wire, and the emergency neutral wire. This configuration enables the emergency lighting to receive power from the normal power source despite the absence of a direct connection. In the event of a normal power loss, the ECI module transitions to emergency power. The connection between the normal neutral and the emergency neutral ensures that the emergency lighting continues to be powered even with the emergency power source operating on a separate derived system. It's important to note that emergency lighting systems are subject to specific code requirements in certain jurisdictions. For example, in the United States, Article 700 of the National Electrical Code, or NEC, provides guidelines for these systems. These requirements often stipulate that emergency lighting must be powered by a source that is independent of the normal power source. Furthermore, the emergency lighting system needs to be capable of providing illumination for a minimum duration, often 90 minutes. Lastly, the system is expected to undergo monitoring for any potential faults. There are several advantages to consider when using neutral bonding in an emergency lighting system. Firstly, it can lead to cost savings. Connecting the neutrals eliminates the necessity for a dedicated neutral connection specifically for the emergency lighting. Secondly, it can enhance reliability. The bond between the neutrals makes sure that the emergency lighting will remain powered even if there's a disruption in the normal neutral wire. Thirdly, it simplifies the wiring. Connecting the neutrals reduces the overall number of wires required, which simplifies the installation process and reduces the time needed. However, it's crucial to keep certain important considerations in mind. One such consideration is that the neutral bond must be implemented at the ECI module, rather than at the panel board or any other electrical equipment. It's also crucial that the neutral bond is not connected to the equipment grounding conductor. Furthermore, the connection should be appropriately sized and properly secured to make sure a reliable connection. In summary, connecting the neutral in an emergency lighting system that utilizes an ECI module offers a safe and effective approach to provide illumination during power outages. It satisfies code requirements, reduces costs, improves reliability, and simplifies the wiring process. Let's delve deeper into the technical aspects of emergency power systems and neutral bonding. Emergency power systems are designed to automatically supply electrical power to critical circuits and equipment in the event of a failure of the normal power supply. These systems are essential for maintaining safety and functionality in various settings, including hospitals, data centers, and commercial buildings. The ECI module acts as an automatic transfer switch, seamlessly switching between the normal power source and the emergency power source, which is typically a generator or a battery backup system. The neutral conductor plays a vital role in electrical systems by providing a return path for current flow. In a balanced three-phase system, the neutral conductor carries minimal current. However, in single-phase systems or unbalanced three-phase systems, the neutral conductor carries the unbalanced current. A properly grounded neutral conductor is essential for safety, as it helps to prevent electrical shock hazards and ensures the proper operation of protective devices such as circuit breakers and fuses. Neutral bonding refers to the practice of connecting the neutral conductor to the grounding conductor at a specific point in the electrical system, typically at the service entrance of the separately derived system. This connection creates a low impedance path for fault current to flow back to the source, which helps to quickly trip the overcurrent protection device and clear the fault. In an emergency power system with an ECI module, the neutral bonding configuration must be carefully designed to ensure proper operation and safety. The ECI module typically has multiple neutral connections, including a normal neutral, an emergency neutral, and a neutral connection for the emergency lighting circuit. The connection between the normal neutral and the emergency neutral is a key aspect of the ECI module's design. When normal power is available, the ECI module connects the normal neutral, emergency neutral, and the emergency lighting neutral together. This allows the emergency lighting to be powered from the normal power source. When normal power is lost, the ECI module disconnects the normal neutral and connects the emergency neutral to the emergency power source. The bond between the normal neutral and the emergency neutral ensures that the emergency lighting continues to receive power, even though it is now being supplied by the emergency power source. The NEC provides specific requirements for neutral bonding in emergency power systems. Article 250.30 covers the grounding and bonding requirements for separately derived systems, such as generators. It specifies the location of the neutral to ground bond and the size of the grounding electrode conductor. Article 700 addresses the requirements for emergency systems, including the need for a reliable power source and the proper operation of the transfer switch. The advantages of neutral bonding in an emergency lighting system with an ECI module include cost savings, increased reliability, and simplified wiring. By bonding the neutrals, a dedicated neutral connection for the emergency lighting is not required, which reduces material and labor costs. The bond between the neutrals ensures that the emergency lighting will continue to receive power, even if there is a break in the normal neutral wire. This increases the reliability of the emergency lighting system and reduces the risk of a complete lighting failure during a power outage. Bonding the neutrals reduces the number of wires required, which simplifies the installation process and reduces the time needed to complete the wiring. There are also some important considerations to keep in mind when implementing neutral bonding in an emergency lighting system. The neutral bond should be made at the ECI module, not at the panel board or other electrical equipment. This ensures that the neutral bond is located in the correct place and that it is properly sized and secured. The neutral bond should not be made to the equipment grounding conductor. The equipment grounding conductor is intended to provide a path for fault current to flow back to the source in the event of a ground fault. Connecting the neutral bond to the equipment grounding conductor can create a parallel path for neutral current, which can lead to nuisance tripping of ground fault circuit interrupters or other problems. The bond should be properly sized and secured to make sure a reliable connection. The size of the bonding conductor should be based on the size of the ungrounded conductors in the system, as specified in the NEC. The connection should be made using approved connectors and should be talked to the manufacturer's specifications. In addition to these considerations, it is also important to ensure that the emergency power system is properly designed and installed in accordance with all applicable codes and standards. The emergency power system should be tested regularly to verify that it is functioning properly and that it will provide reliable power in the event of a power outage. Proper maintenance is also essential to ensure the long-term reliability of the emergency power system. In conclusion, bonding the neutral in an emergency lighting system with an ECI module is a safe and effective way to provide illumination during power outages. It meets code requirements, reduces costs, improves reliability, and simplifies wiring. By following the recommendations outlined above, you can ensure that your emergency lighting system will provide reliable power when it is needed most. Let's delve further into the intricacies of separately derived systems and their impact on emergency power configurations. A separately derived system is an electrical power system that is not electrically connected to the normal power source. This means that the emergency power source, such as a generator, is not directly connected to the utility grid. Separately derived systems are commonly used in emergency power applications to provide a reliable and independent source of power. When a separately derived system is used, the neutral conductor must be grounded at the source of the system. This is typically done by connecting the neutral conductor to a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode provides a low impedance path for fault current to flow back to the source, which helps to quickly trip the overcurrent protection device and clear the fault. The NEC provides specific requirements for grounding separately derived systems in Article 250.30. This article specifies the location of the neutral to ground bond and the size of the grounding electrode conductor. It also addresses the requirements for bonding the non-current carrying metal parts of the system. In an emergency power system with an ECI module, the separately derived system is typically the generator. The generator is connected to the ECI module, which automatically switches to the generator when the normal power source fails. The ECI module must be designed to properly handle the neutral to ground bond in the separately derived system. When the ECI module switches to the generator, it must ensure that the neutral conductor is properly grounded at the generator. It must also prevent any circulating currents from flowing between the normal power source and the generator. The design of the ECI module is critical to the proper operation of the emergency power system. The ECI module must be able to quickly and reliably switch between the normal power source and the generator. It must also be able to protect the emergency lighting circuit from overloads and short circuits. The ECI module must be tested and certified to meet applicable safety standards. In addition to the ECI module, other components of the emergency power system must also be carefully selected and installed. The generator must be sized to provide enough power to support the emergency lighting circuit and other critical loads. The wiring must be properly sized and installed to minimize voltage drop and ensure reliable operation. The overcurrent protection devices must be selected to protect the circuit from overloads and short circuits. Regular maintenance is essential to ensure the long-term reliability of the emergency power system. The generator should be inspected and tested regularly to verify that it is functioning properly. The batteries in the emergency lighting fixtures should be replaced periodically to ensure that they will provide adequate illumination during a power outage. The wiring and connections should be inspected to identify and correct any potential problems. By following these recommendations, you can ensure that your emergency power system will provide reliable power when it is needed most. In conclusion, the proper grounding and bonding of separately derived systems is essential for the safe and reliable operation of emergency power systems. The ECI module plays a critical role in managing the neutral to ground bond and preventing circulating currents. Careful design, installation, and maintenance are essential to ensure that the emergency power system will provide reliable power during a power outage. Let us now discuss the practical applications and troubleshooting aspects of ECI modules and neutral bonding in emergency lighting systems. In practical applications, ECI modules are widely used in commercial buildings, hospitals, and other facilities where emergency lighting is required. These modules provide a convenient and reliable way to switch between normal power and emergency power, ensuring that the emergency lighting remains illuminated during a power outage. When installing an ECI module, it is important to follow the manufacturer's instructions carefully. The wiring connections must be made correctly, and the module must be properly grounded. The neutral bond must be made at the ECI module, not at the panel board or other electrical equipment. After the ECI module is installed, it should be tested to verify that it is functioning properly. The test should include simulating a power outage and verifying that the emergency lighting switch is on automatically. The voltage and current in the emergency lighting circuit should be measured to ensure that they are within the specified limits. If the ECI module is not functioning properly, there are several troubleshooting steps that can be taken. Firstly, check the wiring connections to make sure that they are secure and properly connected. Secondly, check the voltage and current in the emergency lighting circuit to make sure that they are within the specified limits. Thirdly, check the ECI module itself to see if there are any visible signs of damage. If the ECI module is damaged, it should be replaced. If the troubleshooting steps do not resolve the problem, it may be necessary to consult with a qualified electrician. Common problems that can occur with ECI modules include loose wiring connections, blown fuses, and damaged components. These problems can usually be identified and corrected with basic troubleshooting techniques. One of the most common problems with emergency lighting systems is that the batteries in the emergency lighting fixtures fail. This can be caused by a number of factors, including age, overcharging, and deep discharging. The battery should be replaced periodically to ensure that they will provide adequate illumination during a power outage. Another common problem is that the emergency lighting fixtures are not properly maintained. The fixtures should be cleaned regularly to remove dust and debris. The lamps should be replaced when they burn out. The wiring and connections should be inspected to identify and correct any potential problems. In addition to these practical considerations, it is also important to be aware of the potential safety hazards associated with emergency lighting systems. Emergency lighting systems can operate at high voltages, so it is important to take precautions to avoid electrical shock. Always disconnect the power before working on an emergency lighting system. Wear appropriate personal protective equipment, such as gloves and safety glasses. Work in a well-lit area. If you are not comfortable working on an emergency lighting system, consult with a qualified electrician. By following these safety precautions, you can minimize the risk of electrical shock and other injuries. In conclusion, ECI modules and neutral bonding are essential components of emergency lighting systems. Proper installation, testing, and maintenance are essential to ensure that these systems function properly and provide reliable illumination during a power outage. By following the recommendations outlined above, you can ensure that your emergency lighting system will provide safe and reliable power when it is needed most. To further enhance understanding, let's explore some real-world case studies and examples of ECI module applications in different settings. Case Study 1: A hospital uses an ECI module to provide emergency lighting in its operating rooms. The ECI module switches between normal power and a generator in the event of a power outage. The neutral bond is made at the ECI module, ensuring that the emergency lighting continues to operate during the power outage. The hospital regularly tests the ECI module and the emergency lighting system to ensure that they are functioning properly. Case Study 2: A commercial building uses an ECI module to provide emergency lighting in its stairwells and exits. The ECI module switches between normal power and a battery backup system in the event of a power outage. The neutral bond is made at the ECI module, ensuring that the emergency lighting continues to operate during the power outage. The building owner has a maintenance contract with a qualified electrician to inspect and maintain the ECI module and the emergency lighting system on a regular basis. Case Study 3: A data center uses an ECI module to provide emergency lighting in its server rooms. The ECI module switches between normal power and an uninterruptible power supply, or UPS, in the event of a power outage. The neutral bond is made at the ECI module, ensuring that the emergency lighting continues to operate during the power outage. The data center has a comprehensive emergency power plan that includes regular testing and maintenance of the ECI module, the UPS, and the emergency lighting system. Example 1: An ECI module is used in a retail store to provide emergency lighting in the aisles and checkout areas. The ECI module is connected to the store's normal power supply and to a generator. When the normal power supply fails, the ECI module automatically switches to the generator, providing power to the emergency lighting. This ensures that customers can safely exit the store in the event of a power outage. Example 2: An ECI module is used in a school to provide emergency lighting in the hallways and classrooms. The ECI module is connected to the school's normal power supply and to a battery backup system. When the normal power supply fails, the ECI module automatically switches to the battery backup system, providing power to the emergency lighting. This ensures that students and staff can safely evacuate the building in the event of a power outage. These case studies and examples demonstrate the versatility and reliability of ECI modules in a variety of settings. By providing automatic switching between normal power and emergency power, ECI modules ensure that emergency lighting continues to operate during power outages, enhancing safety and security. Regular testing and maintenance are essential to ensure that ECI modules and emergency lighting systems function properly and provide reliable power when it is needed most. The neutral bond plays a critical role in these systems, ensuring that the emergency lighting continues to receive power even when the normal power supply fails. The NEC provides specific requirements for neutral bonding in emergency power systems, and these requirements must be followed to ensure safety and compliance. By understanding the principles of ECI modules and neutral bonding, and by following best practices for installation, testing, and maintenance, you can ensure that your emergency lighting system will provide reliable power when it is needed most. Finally, let's discuss the future trends and innovations in emergency lighting systems and ECI module technology. The field of emergency lighting is constantly evolving, with new technologies and innovations emerging to improve safety, reliability, and energy efficiency. Some of the key trends in emergency lighting include the use of LED lighting, wireless communication, and smart controls. LED lighting is becoming increasingly popular in emergency lighting applications due to its energy efficiency, long lifespan, and superior light output. LED lamps consume significantly less power than traditional incandescent or fluorescent lamps, which reduces operating costs and extends battery life. LED lamps also have a much longer lifespan, which reduces maintenance costs. Wireless communication is being used to connect emergency lighting fixtures to a central monitoring system. This allows for remote testing and monitoring of the emergency lighting system, which can improve reliability and reduce maintenance costs. Smart controls are being used to automatically adjust the light output of emergency lighting fixtures based on the ambient light levels. This can save energy and improve visibility. ECI module technology is also evolving, with new features and capabilities being added to improve performance and reliability. Some of the key innovations in ECI module technology include improved switching speeds, enhanced surge protection, and integrated monitoring capabilities. Improved switching speeds ensure that the emergency lighting switches on quickly and reliably in the event of a power outage. Enhanced surge protection protects the ECI module from damage caused by power surges. Integrated monitoring capabilities allow for remote monitoring of the ECI module's performance and status. In addition to these technological advancements, there is also growing emphasis on sustainability in emergency lighting systems. This includes the use of environmentally friendly materials, the reduction of energy consumption, and the implementation of recycling programs. As the demand for emergency lighting continues to grow, it is likely that these trends and innovations will continue to shape the future of the industry. By staying abreast of the latest developments in emergency lighting technology, you can ensure that your emergency lighting system is safe, reliable, and energy efficient. In conclusion, emergency lighting systems and ECI modules are essential components of modern buildings and infrastructure. By understanding the principles of ECI modules and neutral bonding, and by following best practices for installation, testing, and maintenance, you can ensure that your emergency lighting system will provide reliable power when it is needed most. The future of emergency lighting is bright, with new technologies and innovations constantly emerging to improve safety, reliability, and energy efficiency.